Yeah. Okay. Yeah. Let me just see. Yeah. Okay. Yeah. Thanks again for the invitation to speak. It has been really nice. It has been even nicer that the river didn't ruin my last lecture here. So must be thankful to Mother Nature for that. So I guess. But yeah, so what I have prepared for this lecture is, well, we're going to be talking about stability estimates, but stability estimates for what? But let's just quickly recall the inequality result that we saw like last lecture. Oh, if you have a set of finite measure, a Gaussian window, then I can only concentrate this much on that set, and is inequality sharp. And actually, I'm not sure that I mentioned that, but so this part I mentioned that the only sets where this can be attained are disks themselves, but a consequence of what we did last time is that the only functions for which this can be attained are time frequency shifts of Gaussian. So these are just like, well, you take a translation of a Gaussian, you modulate it, and yeah, these are the only, you have to modulate and translate according to the center of the disk. This is very important. But yeah, but this is the result that we discussed last time. And well, so stability, we're going to be mainly discussing stability of data estimate. And the question is, well, how robust, what kind of information does this actually tell us? So for instance, if we assume that we have a function that almost satisfies equality, right, in that result, for some epsilon sufficiently small, what can be said about the function that we're looking at and the set u? And I don't know, from an intuitive perspective, one would think that, well, since this is very close to achieving the maximum, if the maximum points, if this manifold of Gaussians, of time frequency of shift of Gaussians, or I don't know, if this set of disks is non-degenerate in a sense, we should expect the extremizers, things that are close to extremizing, being close to extremizers, right? So I mean, it makes sense that it should hold, but to which extent, right? That's the main question that we want to address. And well, for those who haven't seen this kind of question before, these are generally known as stability questions for sharp inequality. Well, whenever you have an inequality that you know the sharp constant form, you know exactly what the extremizers look like, you might ask what exactly, well, if I'm very close to extremizing the inequality, do I have any additional information on the structure of these near extremos? And this is actually in calculus of variations, for instance, this helps a lot understanding the geometry of the problems at hand, and also the geometry of the set of extremizers that we're looking at, right? So I think in order to better motivate this thing, I feel like the first time I saw a stability question, I was like, well, that's really nice, it's cool, but what kind of results have people been actually looking into this? And let's maybe take a look at a couple of examples. So the first one is for the isoperimetric inequality. So this is if I'm not mistaken, it's a result from 2010 by Fuscomani and Bardelli. They showed that, well, so let's recall the isoperimetric inequality in dimension 2, right? We saw last time. And we have the equality holds if and only if the set we're looking at is a disk, the ball. But Fuscomani and Bardelli actually managed to extend that. So if this holds, so the set is very close to satisfying to be an extreme over this inequality, then if we define this A of S, which is what we call differential asymmetry of S, this thing is measuring just how much the set looks like a ball, right? So it's basically saying, well, take any Euclidean ball that has the same measure of S and try to fit it in the best way possible to your set S. take a look at what the measure of this symmetric difference is. Then what they proved is that this asymmetry is bounded by a constant. This is a computable constant, an absolute constant, times epsilon to the 1/2. And this is actually sharp. And it's a nice, this is a nice and not too hard observation, that if you take an ellipse, it has a small eccentricity, it's very close to being a disk itself, then this exponent is achieved, right? So it satisfies something like this with equality, so it's going to be for an ellipse, just like the one that I mentioned with a small eccentricity, you're going to be able to satisfy this, and the symmetry is going to be of the order of epsilon to the 1/2 as well. So yeah, so that is one very important example. This was I think that this problem with the isoperimetric inequality has a very rich background. I think it dates back to the 40s, and this was a major over problem in the area. And they solved it in 2010. It's a very celebrated paper. And actually, so this doesn't only hold for 2 dimensions, right? As it's written here, it holds for the isoperimetric problem in any dimension, but yeah, and the same result holds. The constant is going to depend on the dimension, obviously, but let's not care about that for now. And yeah, and let me just mention on top of that later on, actually for an anisotropic version of this inequality, Pigatti, Maggi, and Cortelli actually showed the same thing by using optimal transport methods, which are going to be actually, this is going to come full circle in the end, because we're going to take a look at things that actually require some optimal transport methods, right, in this group. But let's not jump ahead to that right now. So let's move to the next example, which is another inequality that we have seen, which is the Faber-Cron inequality. So the Faber-Cron inequality, as we stated, it just says that if I take the first Dirichlet eigenvalue of omega, then it's bounded from below by the same thing for a disk of same with the same measure. And equality holds here also if and only if omega is itself a disk. But stability version of that also holds, and it's surprisingly an extremely difficult problem. So it was solved 10 years ago by Brasco, Nitilitis, and Delichko, which showed that if your set is almost optimal for this inequality, then the asymmetry, it's, well, what it should be by just considering an ellipse again, and then computing explicitly what everything, what the constants are. But the caveat is that it's a non-constructive proof. So they do prove it by contradiction in a way, which is very, it's kind of well, I don't want to say that it defeats the purpose, because it's an amazing result, and it's nice to know that it holds with that 1/2, but it's a bit unorthodox and sharp in these kinds of sharp stability estimates. So you're basically, what they do is say, well, suppose that you can put that you can reverse the inequality for a certain subclass of sets with a sufficiently large constant, and they actually show that, well, by compactness you can each time improve these sets to be something better. They use results in free boundary elliptic theory in order to conclude that these sets are actually very smooth. They take limits and actually arrive at the case where the set omega is just a perturbation of the ball. At that point, you can just do the computations explicitly and show that you have a contradiction. But it is not constructive, right? So this kind of argument that, well, you just try to prove by contradiction that that if you are close, that you have to have a counterexample, which is a perturbation. It's a bit weird to make it really quantitative, right? But of course, this is still an amazing result, and it's an open problem, first of all, to put a constructive, an effective constant here, right? And the third example, which is another one that we actually saw, and is in these lectures, is that of the Babenko-Beckner-Hazeltine inequality, which says that this holds, right? With this sharp constant, and equality is only if F is a Gaussian. And my first actually showed also about 10 years ago that you can improve it by this factor. And what does it say? Well, you can reorder things and say that, well, if actually f is close by a factor of epsilon to achieving equality here, then it has to be root of epsilon close to the space of Gaussians. And of course, this is again, unfortunately, a non-constructive result. So the methods used by Chris, actually, it's much more than that. It's a two-step method. The first one is needs to use compactness to be able to come to the case where the functions are actually perturbations of Gaussians. That is by far the most difficult part of this paper. It's a beautiful proof. But since he's using compactness, we lose information about this constant. And then you jump at the case where it's a perturbation, there everything is easy because you have a nice structure and so on and so forth. But the usage of compactness here kind of like just says that, well, this constant exists, but we have no control of what that is. Right? So yeah, in light of all of those results, yeah, I'd like maybe to state the main result that we're going to be seeing in this lecture, which is a stability result for the inequality theorem. Yeah, we should perhaps mention that this was a result from I think it appeared published version this year, and it's by my master's student Jaime Gomez, my good friend and my good friends Andrea Guerra and Paulo Tivi and myself. And it actually says the following. So, in contrast, perhaps a bit with the previous case that we're considering, the last two cases that we just saw, there is actually a numerical constant c, such that for any function in L2 and any set of finite measure, if we have almost equality at scale epsilon, then the distance of f to the space of time frequency translates of Gaussians, normalized version of that, is at most this constant times e to the measure of u times epsilon, all that power 1/2. And it's actually a doubly sharp result. It's sharp in this exponent, you can't do better than that, and it's sharp in this exponential rate of growth. You cannot put any constant here, like any beta here in front of this u less than 1. It's sharp in the rate of growth of the constants in terms of the measure of the set and on in terms of the perturbation power. Okay, and yeah, as it stated there, the goal is going to be to understand this proof. And so let's since it's a bit of a long proof, without further ado, let's maybe jump into the main structure of the proof. So the game plan that we have is the following. So we're going to accomplish that in some steps, right? So the first one is, as usual, we reduce to the Fock space, but don't worry too much about this. It's just to give an overall idea of what's being done. We're going to explain each step in detail in a bit. The first one is, well, we translate the problem to the Fock space as usual. So you can just think of an analytic function that is satisfying almost equality in these inequalities for an analytic function that we proved last time. And we can reduce the set by just replacing it with these, at least for this result, we can replace the set by a super level set, right? Where S naught here is going to be the measure of the set we're considering. We're going to replace it by this, the super level set with the same measure, by the same argument as before. It doesn't, it's easy to show that it doesn't violate stability. You only get better from it, right? So, yeah. So the next step is, well, we need some sort of device to prove that the function, if the function is indeed almost satisfying almost equality, then it is almost a reproducing kernel, which are the Bargman Fock, the Bargman transform of these time frequency translates of phi. But if the language of talking about reproducing kernels is a little bit complicated, you can think of, well, f should be close to the function constant equals one, right? So that is the up to time frequency translations. We can suppose that we're around the constant equals one, the constant one function, and we want to show sharp stability for that. So we need something to show that this function f is indeed close to the right order of the constant one. And what we do, maybe in order to draw, it's nice to draw a quick picture. If you recall, we had this function g of sigma, which was like we had I of s is the integral of mu greater than mu star of s of u, and g of sigma is I minus log sigma. So this g sigma function, so this was it was convex and it's graphed with something like that. So, well, what can we do, right? So if we know that we're almost satisfying inequality, it means that there's a point here that is very close to this straight line, right, in the graph of G. So it does something like this, but in a convex way. And we want to show that under that condition, we actually can say more about the function G. We can actually tell some more stuff about it. And since it is convex, this is actually true. There's a point inside the interval for which we almost have equality. Well, then you can actually look at the derivatives at the endpoints. If they cannot be too wild, they have to be well behaved. If you take a look at the derivative of G at, if I'm not mistaken, at 0.1, this is going to be a multiple of the derivative of I at 0.1, which is just the supremum of this function u. In particular, if this point is very close to the line, then this derivative here, so the slope of the change at the graph of t here has to be almost equal to the slope of the graph of the straight line. And since that holds, you can quantify everything in a very nice manner. And since that holds, you would have at the end of the day that this I prime of 0 is very close to 1. I think, yeah, we have to be a little bit more precise, but the thing is that this I prime of 0 is very close to being 1. But I prime of 0 is just the supremum of u, which we know since f has Fock norm 1, this is actually at most 1. So then we have something like that. This is actually equal to 1 minus the L infinity norm of u, and it has to be small. So we know already the first step so the first observation, the first remark is that from this picture, this quantity there, 1 minus the L infinity norm of the function u, has to be very small. So u has to be very close to being a constant function, at least in L infinity norm. And we want to kind of extrapolate this knowledge to integrals as well, right? So we want to extrapolate it from the L infinity case to the L2 case. And the first step that we have, so the second step that we have is to show that actually this difference here bounds the L2 difference between f and a constant. So it is kind of weird. It's kind of a reverse triangle inequality because this is bounded by the difference in L infinity of u and 1, and one would argue that that should be very close to the L2 norm. But we can do something like that, and the proof, as a matter of fact, it's not too hard. We're going to see next. So the first step is that we work with what we have. What we have is a bound for that shows that how the L infinity norm is close to 1, and we can actually improve that to a bound on the difference in L2, on the distance in L2. Okay, so but by this argument, it is enough to show that this difference is bounded by a constant times e to the measure of u times s, right? Because, well, we showed that it is an upper bound for the L2 distance. if we show that this inequality holds, that this 1 minus L infinity norm of u is bounded by something like this, we're good. Okay, but then in order to do that, we just fix d star of s equals to e to the minus s, which is just a rearrangement that we obtained by looking at the extremals, right? So the extremals are the reproducing kernels. If you look at their radially decreasing rearrangements, or well, let's say the one-dimensional rearrangements, it's going to be exactly e to the minus s. And the next idea is to look at these quantities. Why? Well, we can do an explicit computation. Do an integral from 0 to s naught of e to the minus s times u square of s. What is this? So this is the derivative. We recall that this is the derivative of I prime of s. So this is just 1 minus e to the minus s naught minus minus f0. Right? So this vanishes, you're going to get something like this, which on the other hand is just in this integral. So this integral right there just measures exactly the deficit. It measures how far we are from maximizing the inequality. So looking at it seems like a good idea. And as a matter of fact, we're going to show that if you put absolute values inside, it is bounded by the deficit still. We can find actually it doesn't really matter. This part is not where the really hard part of the proof is. It's just saying that, well, you can replace the deficit by this other deficit in order to prove this, right? So we recall that the previous step gave that we want to show that this is less than that. Well, we do an additional step in the middle. Well, let's show that this is less than something like this, right? Instead of showing that it's less than the deficit. Yeah, so this is not extremely hard. It still uses the proof of inequality in a nice way, though. So we're going to see in a bit. And finally, the crux of the argument is inequality. So it's basically showing that this kind of deficit, this modified deficit, bounds the distance in the supreme norms, for some numerical constant. And in order to do that, we actually need something a little bit stronger. We will not put S naught, which is the measure of the set U, but we'll put something like a different parameter here as star. This S star is going to be sorry, this should be S star. The point where the graphs of these two functions intersect, we're going to show that, well, incredibly, these functions intersect. So there is an interval where one lies above, and from that point on, one actually they change signs. So this point is well defined, and we're going to need an estimate for this as star point that we're replacing there. And in order to do that, we need an improved level set estimate. So this is the more technical part of the proof. But that is kind of the whole idea behind it. We could control the supreme norms by just looking at the graph, and then we're like, well, the only information we have is in the supreme norms. We can actually control something with that. We can control them from above, so everything looks fine. So we need another bound, right? So that's what we're seeing in this. Okay, so let's maybe try to take a look at the first steps of the proof. So the first step, as we said, was not too hard, the translation to the box spaces. So let's just jump at this the second step, where we showed that actually the distance, so 1 minus the supremum actually controls the L2 distance, right? And this is surprisingly also not too hard. So we just well, what can we do? We have an L2 norm. We can expand it, of course. That's the most perhaps naive idea that we have. By expanding that, since these functions right there have norm equal to 1, and since the function f that we're considering also has norm equal to 1, the expansion actually simplifies to this. Okay, but then what is this? So this is these F Z naught, they're just a multiple of the reproducing term. So whenever we take these inner products, this is going to be just F, it reproduces F at Z naught times the Gaussian factor. And hence, when we want to control this L2 difference, it's an identity, just 2 minus twice times the real part of the C bar constant that appeared F of Z naught e to the minus times the Gaussian factor. Okay, so then we take C that minimizes this last term. So this is just basically taking like e to the I times the phase of this complex number. You just get this, which is exactly 2 minus 2 times the root of u at Z naught. In order to minimize this, we need to maximize this, which yields the supremum term that we have, and it yields this first inequality, and the second one is just well, it's just a direct inequality, right? That we have. Okay, so then, well, it's a very simple lemma, but it turns out to be extremely powerful that we can replace the L2 distance by an estimate between the distance of the supremum, right? So we need to show that if the suprema are closed, then actually the functions are we show that if the suprema are closed, then the functions are closed. We need to show that, well, if the functions are closed in terms of the deficit, then the suprema are closed. That's what remains for a suprema. So that is step 3. So for step 3, we actually need to recall what we proved last time. And how is that? Well, let's just recalling the function I of s that we had before. We had this, we proved this inequality last time. I prime plus I double prime greater than or equal to 0. But this is an inequality about the distribution function of u in disguise. How? Well, if you recall that I prime, as I said, is just u star of s, and that u star is just the inverse of the distribution function, then you can just play around and rewrite this inequality in the following form. Okay, so this is just this is going to be 1 over u star prime. This is minus 1 over u star. U star prime is just I double prime, and this is just 1 over I prime. So you reorder, you see that well, this thing is actually negative. When you invert inequality, the inequality sign changes. So, well, you have something like this for all s greater than or equal to 0. And since this is an inverse function, well, the equivalent form is that the distribution function, when you take its derivative, it's less than or equal to minus 1 degree. So this is really an inequality about the distribution function of these functions u. Right. Right now we take a look at mu of t minus log of 1 over t. We differentiate it, and we see actually that this derivative is actually less than or equal to 0 because of this one. Okay, but what does that give us? Well, it actually tells us that, well, since one important fact is that the integral of those two parts are the same over the positive line, wherever both of them are positive and so on, then actually, well, the integrals are the same and it's a decreasing function. Therefore, there is a point t star up until which this function mu of t dominates log of 1 over t, and from that point on, it is dominated by that. So the picture is something like this. So you have, so this is maybe mu of t, and this should be like log 1 over t. They have the same integral, so there is a point here, which I'm going to call t star, at which they intersect, and the inequality flip side. So the relationship of who wins against whom changes, right? Okay, so that is it's a nice observation, but what is that good for? Oh, it actually can show, it can help us show what we wanted about these differences. So just before that, we take S star to be the point where basically U star equals e to the minus S. In other words, if you translate between the rearrangement and the function and the distribution function itself, T star is equal to the minus S. And our first lemma is that we can control this integral here by still the deficit times an exponential vector. Well, if I put S naught here instead of S star, by this argument here, this would be true. But the whole point is that I need to put something slightly different, which is exactly this geometric point where the graphs interact with one another in a non-trivial way. But it turns out that the proof is not actually that complicated. So let's maybe take a look at the proof. So the real difficult case is when S naught is greater than S star. So the other cases are easier. And the crucial observation is that this ratio between U star and V star is increasing. Why? Well, this is just another way to write this in. So this ratio is increasing, and we have that the integrals are equal, right? So that is also what caused the Z star to exist in the first place. Okay, let's go and try to prove that. So first of all, let's look at what this actually is. Well, by looking at the definition of epsilon, it was something like that. But then this is actually equal by the fact that the integrals are the same, and the fact that instead of integrating between 0 and S naught, I can integrate between S naught and infinity. I have an identity like this. Okay, but then, well, I know that the ratio is increasing, so I write it as something like this. Oh, it's just it is actually an identity between this integral and this one. But this is increasing, therefore this is at least 1 minus 1 over r of S naught times this integral. On the other hand, if I want to bound the integral between S star and S naught, then I can do the same thing, but I get a reverse inequality with this 1 minus 1 over r of S naught factor and an integral factor. Okay, but now I have something that says that this factor right here is bounded by constant times epsilon, and I have something that says that this factor right here bounds the kind of discrepancy that I said before, which between S naught and S star. Okay, so putting them together, we get that this remaining part that we don't know how to bound is actually bounded by a multiple of epsilon times a constant here, and then the rest is just algebraic manipulations. So we knew how to bound between S naught and infinity. We now know how to bound between S star and S naught. We sum both of the bounds, we get something like epsilon times this. And when we reduce and take a look at what the constant is that it's unit by that, we're going to see that it's exactly integral between 0 and S naught of V star, which is bounded by 1 because V star is positive, and we can replace S naught by, and then its integral is 1. And underneath we have the integral between S naught and infinity of V star, which is e to the minus S naught. So this just reduces to the following inequality, and we have proved the result. So this is perhaps a technical, a slightly technical proposition, but it actually drives the point home that you actually can replace the point S naught by this point of intersection S star, right? Okay, good. So we have that, and now we need to move to the final step. And in order to do it, recall what we need to do. So just before. We proved that this integral here is bounded by epsilon times the constant, times the right constant. Now, in order to finish the result, since we proved that 1 minus the supremum bounds the L2 distance, I would like to say that this guy bounds 1 minus the supremum, right? So that is the missing step. That is the missing inequality. So I would like to say that this is at least 1 minus t times a small absolute constant. In order to do that, maybe it's a good idea to look at the distribution function, right, and get some good estimates. Because in order to understand how how U star deviates from the exponential, it would be a good idea to understand how the distribution function, which is just the inverse of U star, actually deviates from log of 1 over t, which is, well, those two things are equivalent. And actually, this proposition gives us an upper bound, a very concrete upper bound on that deviation. It just says that the distribution function, if I'm very close to, well, t here is just a supremum, as usual. So you can understand the theorem as follows. So if I'm very close to fulfilling that the supremum is close to 1, then the factor that I lose in estimating the distribution function is a factor of 1 plus absolute constant times this discrepancy times the log of capital T over T. So yeah, that's basically, so in this log of capital T over T, it's very similar to log of 1 over T, which is the inverse of e to the minus s, which is directly related to the extremizer. So in a sense, we're saying that if our functions are very close to being an extremizer to our inequalities, then the distribution functions have to satisfy some very, very nice bounds. For now, let's just assume that result and see how we can conclude. So yeah, so let's just, so as mentioned before, what we need in order to finish is this lower bound. So we can pass to inverse functions, right? We just do a change of variables here. And by doing that, we actually get that it is sufficient to prove that the integral between t star as defined on the blackboard in here and the supremum of log of 1 over t minus mu is actually at least 1 minus t. So in order to do that, we need to prove a couple of things. Right? T star cannot converge to 1. Otherwise, this integral would be super small and would be, there would be no hope of proving a result. So the first thing that we need in order to do that is to show that T star actually remains bounded when the supremum goes to 0. So that can be achieved actually it's not too hard. So basically it's just, well, T star is the point where the distribution function equals log of 1 over T star, right? That's just the definition by the intersection of the graphs that we had before. But then we have an estimate on the distribution function. The estimate looks like this. We can reorder stuff. We can take a look at what exactly this inequality is saying in terms of T star. And after reducing, we get that T star is bounded by something like this. And since T is between 0 and 1, this is bounded by e to the minus 1 over C naught, which is definitely less than 1, because C naught is an absolute constant. So we replace, and since we want lower bounds, we can just say, well, okay, T star is smaller than that. So we can put, it's in particular smaller than 1 over e to the minus 1 over 2 times C naught. So we just want a lower bound for this, of this kind. Okay, so that's all we want to get. And actually it's essentially done from this point. We use the upper bound that we have in mu, which is exactly this. We expand out what the logs are, what they look like in this regime. And as a matter of fact, you're going to get something like that this thing here is bounded from below by 1 minus t over 2 in this regime. Well, and then you just take it out of the integral, it's 1 minus t over 2. And here you have just capital T minus this guy, which is just the integral of 1. Okay, this is an absolute constant because you can assume that capital T is sufficiently large. Hence, what we get at the end of the day is that indeed this has a lower bound of the form C times 1 minus T. And yeah, so then this morally finishes the proof, except for the part that I didn't prove the proposition, right? And the good news for you is that I won't prove the proposition. Is that, oh, good and bad news? I don't know. The good news because it's a bit technical. But the bad news is that well, it has kind of the last remaining main idea of the paper, which is, well, we're looking at measures of super level sets of things that are very close to being to being constant, right? So function is very close to being constant. So if T, if the level set that we're analyzing is kind of sufficiently close to being at the top, right? At the supremum, then we can actually say that the function that actually the level sets of U are going to resemble those of the exponential of the Gaussian. So it's going to be just you can show by some geometric arguments that these level sets where U is greater than T are just perturbations of the level sets of the Gaussian. So in other words, you remember what I said before about the level sets, the case where you just reduce the perturbation being crucial in the other cases, but then you lose an explicit constant due to convections. This doesn't happen here. We reduce to the case where we're perturbing, and hence we can just use calculus of variations, right? So the techniques from calculus of variations to finish. Well, this is just the level set for U is greater than T is just a perturbation now of a ball. So we can basically write out explicitly what it is in terms of the perturbation. We can do several computations, and we can get we can get a very, very precise control in terms of how it deviates, to which extent it actually is a perturbation of the ball, which is actually reflected in this inequality. So yeah, that is more or less the idea of the proof of the proposition. Well, if you are curious and want to read the paper, I must warn you that it's not explained perhaps in this way in the paper itself. It is written in a way more technical, language, but the idea behind it is that, exactly that. It's that, well, whenever your function in supremum, the supremum of your function is almost one, your function has to be a perturbation of the constant function, and hence its level sets have to be perturbations of the level sets of the constant function, and you can quantify that in a very, very precise way. Okay, but that's not everything, right? So we still need to show that it's sharp, and unfortunately, since we wouldn't have time in any case to show that the proof of the proposition. The proof of the proposition actually has the core of the argument to why everything is sharp. Unlike this Laplacian case where just for ellipses you can basically compute what the eigenfunctions are, here you need the problem is slightly more nonlinear, right? So we have to basically control how under small perturbations these super level sets behave. It's still possible. I'm not trying to say that it's absolutely nightmarish. It's not. It's possible, but it takes a little bit of extra work. So the counterexamples that we have are actually very simple functions. It's just a second. You just perturb with a polynomial of degree 2, the constant function, and you see that actually these sets you can actually control very nicely how much they resemble disks. And as a matter of fact, these functions are of order epsilon away from the constant function, but by controlling these level sets, you can show that this difference, which was exactly the deficit we wanted to control, is bounded by something like s times e to the minus s epsilon squared. This is this is exactly where the exponential factor is coming in. So it shows that, well, in order to improve the constant in our main result, the only possibility is that you put an additional polynomially decaying factor on s. Other than that, there is no way to improve the constant in front. There is no better exponential decay that we can have. This is kind of the overall idea. Of course, the execution is a little bit messier than that. We need to really control well how these things deviate from disks and so on and so forth. But I think that's kind of explains the main ideas behind the proof. Okay, so just as maybe a last remark in the main theorem is that, well, you might have noticed that I stated all of the theorems before. So the first theorems that I was discussing were the isoperimetric inequality, the Faber-Kronig inequality, and the Hauser-Fiown inequality. And in one of them, it's a functional relationship, and in the two other ones, it's actually a statement about a set. Here, in this short time for a transform context, it's about both. But the main result I've proved so far only talked about the functions, right? So what about the sets? So what is we deduced so far that if we almost attain equality and then equality result, then actually our functions must be close to time frequency shifts of Gaussian. But what about the sets? Are they close to disks? And it's also another result by that we managed to prove, that you can actually control the same Frankel symmetry by the right order of exponent. And well, we have this constant, which is explicitly quantifiable, but more on that constant maybe later. And it is sharp on the exponent of epsilon. The sharpness is basically here. So you just take u to be these sets. Already proved. The way to prove it for general sets, which are not super level sets, it's a bit more complicated. And that's where I said that the transport map would come back to this topic. So in order to say that, well, actually, we can't do it for arbitrary sets instead of just super level sets, the idea is just to transport the portion in this super level set that is not in U to the portion in U that is not in the super level set. In other words, so a picture would be something like this. So we have our set, the business A of U, and then U might be something like this, but it might have some kind of additional parts, right? So then we just ignore this intersection here that we have, and we look at the differences. So the idea is then, well, let's take an optimal transport map between both of them. And don't get discouraged by this, it's just a map that basically transports one measure to the other, that you can change variables between one and the other. This exists. It's we don't need even any kind of, well, we need only that this map is measurable. We don't need any fine properties of that. It's just a very, it's just a better way of formalizing this argument. So take a map that transports one to the other. And why are we taking that? Well, because, as I said, it transports one measure to the other. So if you integrate u of t of x over a set, it's just the integral of u over t of that set. That's what the transport map does. The idea is, well, it's two main parts. The first one is, well, whenever the transport map lands close to the point itself in terms of magnitude, we should be good. When it lands far away, then you have to control that set. And it's exactly what we're doing here. So take the set where the transport map lands far off by a certain factor from the radius of the point x, right? From the norm of the point x, sorry. So by definition, we take a look at these differences. So we just use the fact that it's a transport map indeed. And then, well, this T of B and B, you can replace it by A of U and U. And as a matter of fact, so since we know that the integral of 1 minus the integral of U over the set U is small, we know that the difference between these two has to be small because this one is larger than that, and it's also bounded by 1. So we say that, well, this is bounded by the deficit that we had before. On the other hand, so the argument right now is essentially doing what I was indicating before. The function u is morally a perturbation of the Gaussian. Since it's a perturbation of the Gaussian, we can think of, well, like if you replace u of x by e to the minus pi x squared, then this inequality right there would say that this difference between u of x and u of t of x has to be large, and that is basically what we're doing. It's just that we need to quantify how much it actually deviates from the constant function again. But the idea is basically in this set, you have good bounds for this difference. And indeed, this implies that the measure of that set is small. So you have good bounds for this difference, but on the other hand, we have proved that the integral of this difference on the set B is bounded by epsilon. Sorry, here should be gamma, not epsilon. Sorry about that. So then we get to a bound on the set, on this exception of set B. And the remaining part is just the set U minus T of B. But that's exactly as I said, the set where the transport map length is close to the point itself. If it's close by, then everything works very nicely. And you can basically just think of U as A of U itself. So it's not very difficult to show that this difference right here is bounded by gamma. So if you put them together, you're going to see that the symmetric difference between U and A of U is of the order epsilon over gamma plus gamma. Take gamma to be like root epsilon. You get that U is epsilon to the 1/2 close to the set A of U. And finally, this set A of U, as we indicated before, it's a perturbation of the ball. So if we, again, by variational estimates, we can show that this is epsilon to the 1/2 close to being a ball, and this finishes the proof. Yeah, so that's basically the idea. Of course, again, I'm sweeping many technicalities under the rug, but let's not talk about that. And let's instead go to a couple of remarks, first of all. So first of all, this has been recently generalized in the case of curvature 1. So that is a case where we're working on the sphere that I mentioned last time by Garcia Carrero and Ortega Pedra. And well, together with Jaime, David Palayo, and Pedro Melinkiewicz, we are finishing a version where we actually can do it for the hyperbolic case, so a stability result for the wavelet transform as well. And it's the nice part is that it's actually uniform on the parameters. You get a very good bound. We can recover by our proof that this result in the Fock space is a limit. It's also I should, in order to do it justice, I should mention that they are like Maria Angeles and Joaquim also managed to get the Fock space result as a limit. But they have only one parameter to try to keep track of in order to get uniformity. Here, if you recall this alpha parameter in the Bergman space, it was greater than -1. So you have both two degenerate cases when it's going to infinity and when it's going to -1. We need to take care of that. This is a little bit more technically complicated, but that's it. And finally, the last consequence of this circle of ideas, let's say, is that Hubert, Frank, Fagunipol, and Palatini managed to use a result in order to prove a sharp stability version of the Verrill entropy inequality. So this Verrill entropy inequality, for those who don't know, actually says that this quantity there is minimized for F equals a Gaussian. And this actually solves a question by Lieb. Lieb was the first person that actually proved this Verrill entropy conjecture in the 80s. Well, further you tell, his proof does not really, it doesn't even characterize the extremizers, let alone yield any kind of conceivable hint at what kind of a stability result would be. Then I think Carlin managed to prove the same thing and characterize the extremizers, but it's also well, the stability version also is it's not evident how to get it from Carlin's result, from Carlin's proof. It's a proof that really heavily works on a couple of nice identities about gradients of the modulus of an analytic function, but needed something else in order to be able to show a full stability version. And they were able to do that by using basically a result of as a black box, actually. And there's actually two ways. One is using as a black box, and the other one you can develop a different theory for these for what they call, I think, in physics, the coherent states. don't ask me about that. I don't know too much about it. But yeah, so these are the remarks that on this last result. And maybe let's just finish this lecture series with some open questions, right? So look, I'm trying to. So these are going to be like in somewhat increasing order of I don't know what I think of as a figurative, right? So the first one would be, well, as I said, I would talk again about this concept in the set stability. The exponent is short, but the constant is not, most likely. So the first question is, can you improve this constant here to something like e to the measure of u? So replace this 3/2 by 1. That's the first, it would be a completely sharp result, both in the exponent and on the constant if one managed to do that. Then the second one is, well, can something be said about local maximizer for the Gauss transform problem? So if instead of wanting to globally maximize the concentration like Fabio Paulo did, if we want just to analyze what local maximizers are, what are their structure? They still need to be disks? I think this would be like the next natural step from the point of view of calculated variations for this problem. And about localization operators, so just coming back to another previous lecture, well, given a function in L2, is there a domain that has this function as an eigenfunction of its localization operator? It's kind of an inverse problem. Like you give you a function, you're supposed to construct back the domain. You don't expect this domain or class of domains to be unique or to prove to yield any uniqueness of that kind, but I think it's an important problem because, as I said, the problem of constructing eigenfunctions for localization operators is really hard. And I think the only reference in the literature so far is this by Dogashi, where she manages to prove it for disks. But even if you take an ellipse, you have no idea what it looks like. And finally, the last two questions, which I hope that one day will be solved, are the following ones. So maybe the question that would be the most important as a general result in this area is, well, fix a window function. Can we construct a non-increasing function h of g such that whenever we have concentration at level 1 minus epsilon at a set u, then the measure of u is at least hg of epsilon and hg explodes at 0. I think a non-constructive proof of that should be possible, still would be heavily appreciated. It would beat Leib's uncertainty principle, it would beat these weak uncertainty principles in the literature. But the whole deal with this is just constructing a function that satisfies that. So proving a really an effective bound of that. So doing it in a non-effective way would be also already a very nice partial progress, but doing it in an effective way would be the ultimate goal. And the last question is what happens to optimal concentrations for different windows. So let's maybe not look at the Gaussian, but look at all Hermite functions as windows. Can we characterize exactly what the extremals look like? Hermite functions are also very particular in this context. And well, you have lots of structure that is yielded by the short time Fourier transforms with them as windows, but the real, so already solving it for Hermite functions would be a major step, I would say, but doing it for a function that is not a purely Hermite function, maybe, I don't know, consider a linear combination of the first and second Hermite functions and try to prove an optimal concentration result. I'm not even sure the disks are the optimal sets. I would actually be surprised. So this is kind of the ultimate dream in this theory, to prove that an optimal concentration result for any window, just kind of be able to characterize, say that, well, there are extremizers, the sets look like this. If you give me a window, I can actually concentrate can construct the best possible function h of g that satisfies that. This would be the the perhaps unattainable dream, but well, one can only dream, right? So, yeah, that's all I can say, I guess. Thanks.
Thank you. Thank you very much. It's time for discussion. If you have any questions, please ask. Any questions? If you have some questions later, you can ask them later. Lecture, and then let us thank João for the whole series of lectures.